Okay, well, hello. Today I'm going to talk about an introduction to what stoichiometry is, define it, kind of give you an analogy. We did an activity yesterday over Zoom. It's very similar to that, but it's going to be dealing with moles and some calculations. So today's objective: what's the importance of a mole ratio in our stoichiometric calculations, and then finally, can you find the mole ratio in a chemical equation between two substances? So, stoichiometry, what is it? It's a proportional relationship between two or more substances, and you use it during chemical reactions. Basically, it's the art of figuring out how much you can make without actually doing the experiment, or figuring out the mass that comes out without actually weighing anything. So it's kind of a math heavy chapter. Now, your book does mention that there are two types: composition stoichiometry, which deals with mass relationships. So back to our wheel toothpick models, if I asked you to weigh the wheel and the toothpick, you could figure out how much mass you can make from a chemical reaction. And then the reaction stoichiometry kind of deals with between reactants and products, like what comes out of it. This is elements within a compound. I guess I should have specified that. And this is reactants to products, or vice versa. So yes, stoichiometry, the art of counting without counting, the art of weighing without actually weighing anything. So to solve any stoichiometry problem, you need a mole ratio. And that is why this lesson is solely about figuring out mole ratios. It's going to be your conversion factor. You're going to figure out the amounts of moles of any two substances and figure out the proportion between the two. So if I have an equation here, 2 aluminum oxide liquid form decomposes into 4 aluminum solids plus 3 oxygen gas. These numbers in the front actually represent moles. So I actually have 2 moles of aluminum oxide breaking down to produce 4 moles of aluminum and 3 moles of oxygen gas. So to show the relationship between all of these compounds, I can use mole ratios. So if I wanted to look at aluminum oxide and aluminum, so here's aluminum oxide, here's aluminum, I actually have 2 types of mole ratios. If I was in aluminum and I wanted to go to aluminum oxide backwards, my ratio would be 2 moles of aluminum oxide to 4 moles of aluminum solid. And the reason for that is you have to think about what you are given. If you are given aluminum and you want to figure out how much aluminum oxide can be produced, well then you put your given here times, and then whatever compound or element you are in, that goes on the bottom, so it cancels out. So that way you are left with the product or whatever element or compound you're trying to figure out. So 2 to 4, or I can flip it, if you're given them aluminum oxide and you want to figure out how much aluminum, it'd be 4 over 2. So moving on to aluminum oxide and oxygen gas. There's a relationship between here and over here. So if I'm in oxygen gas, okay, so I'm given oxygen and I want to get to aluminum oxide, oxygen better be on the bottom, aluminum oxide on top. So my mole ratio is 2 to 3. But you can also flip it, okay? So 3 to 2. So it kind of depends on what you are given or what you are in and you're trying to get to. So whatever you are given or in, that goes on the bottom. Okay, last relationship here, because I've already done aluminum oxide to aluminum and aluminum oxide to oxygen, you can actually write a mole ratio between the two products, aluminum and oxygen. So aluminum and oxygen gas, if you are in oxygen, oxygen better be on the bottom. So that ratio would be a 4 to 3. Or flip it, if you're in aluminum and you go into oxygen, 3 to 4. So take some time, work through this, make sure you understand why you can flip it and in what circumstances you'd want to flip it. Now let's say that I have 13 moles of aluminum oxide and I want to know how many aluminums I can make. It's so weird saying aluminums, aluminum ions, no, aluminum atoms, I don't know, whatever. So there's some steps. First off, identify the amount of moles that you know. So in this case, I know I have 13 moles of aluminum. Okay. Using coefficients from the balanced equation, set up the mole ratio with the known substance on the bottom and the unknown on top. So what that's going to look like is I start with what I'm given. 13 moles of aluminum oxide. I want to get to aluminum. So my mole ratio should be 4/2. 4 moles of aluminum, 2 moles of aluminum oxide on the bottom. And the reason for that, again, is because this is going to cancel out with that. And you're going to be left with moles of aluminum as your unit. All right, so then you multiply across. 13 times 4 divided by 2. Punch that in a calculator. You should get 26 moles of aluminum because that is what's left. Now, make sure your equation is always balanced, okay? A lot of times the book will give you a balanced equation, but sometimes they can be sneaky and they don't give you one. So I guess I should have checked that first. 2 times 2 is 4. 2 times 3 is 6. 3 times 2 is 6. Okay, this is a balanced equation. Here's another example. What are the mole ratios? Looking at nitrogen and hydrogen gas to form ammonium. So nitrogen gas to hydrogen gas, we're going from here to here. Let's say that you are in hydrogen gas. So hydrogen better be on the bottom, so it should be a 1:3 ratio. Or flip it, if you're in nitrogen gas and you're going to hydrogen, 3:1. Nitrogen gas and ammonia. If you are in ammonia and you're going to nitrogen gas, ammonia better be on the bottom. So it should be a 1:2 mole ratio. You flip it, 2:1. Hydrogen gas and ammonia. Here's hydrogen gas. Here's ammonia. Let's say I'm in ammonia. It better be on the bottom. So it should be 3:2. But if you're in hydrogen gas, it'll be 2:3. So how many moles of ammonia can be made with 2 moles of hydrogen gas? So you start with what you're given. You were given 2 moles of hydrogen gas. The next step is, what's your mole ratio? Actually, I forgot to check. Is this a balanced equation? N2, I got 2 N's, 2 N's, 6 hydrogens, and 2 times 3, 6 hydrogens. Yes, it's balanced. Okay, so start with what you're given, 2 moles of hydrogen gas. I'm in hydrogen, so that needs to be on the bottom. And then I'm going to ammonia, so it should be a 2:3 ratio. Now you just multiply across. 2 times 2 divided by 3, 1.33 moles of ammonia. Okay, because the hydrogen is going to cancel out. All right, so we'll see here. Got some more examples. How many moles of H2CO3 can be formed from 2.57 moles of carbon dioxide? So, start with what you're given. 2.57 moles of CO2. And this is a balanced equation. My ratio is going to be 1:1. So my answer, 2.57 H2CO3. And I forgot to write moles. Shoots. So make sure you write moles. How many moles of oxygen gas are necessary to completely burn 4.33 moles of C3H8? So this is my given. Right here. Start with that. Make sure the equation is balanced. It is balanced. I'm just going to let you know it is balanced. So start with what I'm given, 4.33. I want to get to oxygen. So C3H8, if I look here, 1's going to be on the bottom. I'm going to oxygen. 5's going to be on top. 4.33 times 5 divided by 1, 21.65 moles of oxygen gas. What if I would have known how much carbon dioxide can be made? So again, you start with what you're given. Set up your mole ratio. I'm in CH38. So 1's going to be on the bottom. I'm going to CO2. 3's going to be on top. 4.33 times 3 divided by 1, 12.99 approximately. Don't worry about SIGs. What if I want to figure out how many moles of water can form? Start with what you're given. Look at the mole ratio. C3H8, 1 better be on the bottom because that's what I'm in. I'm going to water. 4 is going to be on top. 4.33 times 4 divided by 1, approximately 17.32 moles of H2O. So that is just a short little lesson on mole ratios. You do have an assignment, a worksheet. It's a single-sided. It's 9.1 mole to mole stoichiometry worksheet. This will be due Thursday, I think, at noon. So let me know if you have any questions.